All right, so now what we are going to do is to take a look at how we represent chemical reactions. So when we talk about representing chemical reactions, what we use are things known as chemical equations. All right, so we can say that chemical equations, and we'll abbreviate equations from this point onwards as EQN, represent chemical reactions, which are just chemical changes. And remember, we abbreviate chemical reactions or reactions generally as rxn. So you can think of a chemical equation. Now you may initially think of it as similar to a mathematical equation, but it's not a math equation. There aren't any equal signs in it. You can think of it more like similar to a chemical sentence instead of a math equation. Now there are elements to a an equation, like in a strict sense, in a chemical equation, but we'll see some differences here in a second. So it's similar to a chemical sentence, and we'll give you an example here. So we can say, for example, that we can say hydrogen gas reacts with oxygen gas to produce liquid water. Okay, so that's a fairly straightforward normal sentence that we might be familiar with. We can take that and we can turn it into a chemical equation that represents the same information, but we don't lose any of that. And we can write it in a much more concise way. And this is what we're going to do. So we can say hydrogen gas. We'll try to color code these. So hydrogen gas, we know now at this point, hopefully, hydrogen gas exists as H2. It's a diatomic molecule. And then that is going to react with. So when we see the phrase reacts with, we actually use a plus sign. So we can say hydrogen reacts with, and then we have oxygen gas. So oxygen gas is O2, diatomic, just like hydrogen is. And then the key thing here in a chemical equation is this phrase here, to produce. And the to produce, we use an arrow. And that arrow always points from the left side to the right side of the chemical equation. And then we produce, what do we make here? We make liquid water. Okay, so our liquid water is going to be H2O. And that equation that I just wrote, I haven't lost any of that information that was in that original sentence that I came up with at the very beginning. Now, there are a couple things that I'm going to add in to this equation just to be a little bit more precise. So we can say hydrogen gas, and I'm going to represent the physical state of the hydrogen here with something with a symbol in parentheses. So the G there would mean that it's a gas. Oxygen gas would be O2, also followed by a G in parentheses. And then water here is a liquid. So as you can imagine, I'm going to use an L in parentheses for liquid. All right, so that is your general way in which your equations are going to look, your chemical equations are going to look. And again, I haven't lost any of this information here that I wrote in my normal sentence when I convert it into a chemical equation. All right, so when we orient ourselves with a chemical equation, there are a few things to keep in mind. So this arrow here always points by default from the left to the right. Okay, and you can think of the arrow as meaning produces or yields or gives. That's what it represents. On the left side of the arrow, whatever we have there, these are called reactants. So they're on the left side of the equation. And then on the right side of the equation, we have what are known as products. So products are on the right side. So the reactants on the left react together to produce products on the right. If you have multiple reactants or products, separate them. So that's what you see this, the plus here, that means reacting with to give, reacting with the oxygen to give H2O. The things that I'm going to highlight here, the G as well as the L's, those are known as state symbols. Parentheses after the chemical formula for the reactant or the product. Okay, and the state symbol, as you can imagine, give us an idea of that's the physical state of the reactant or the product. Okay, so we use two of those state symbols in our equation. Let's list all of them. So we have solids. So solids are abbreviated, or the state symbol for a solid, I'm sorry, is S, lowercase s in parentheses. A liquid, or abbreviated lowercase l in parentheses. Gases, or abbreviated lowercase g in parentheses. And then there's a fourth physical state that we call aqueous, and that's abbreviated AQ. And then what this means is that whatever that substance is, it's dissolved in water, in H2O. Okay, so we're going to see all of these four physical states and these state symbols in our equation whenever we write them. There are a couple other things, or one other thing that we may see in our equation. So we can say sometimes special conditions we'll see is a triangle, either above or below the arrow. And whenever you see this triangle in a chemical equation, what this means is that heat is needed, required for the reaction. Okay, and we're going to come across several of these down the road. If you go into higher levels of chemistry, you'll see other conditions written above and below the arrow. That is generally how those conditions are shown in a chemical equation. All right, so we have our basic layout of our equation. Reactants on the left side of the arrow react together to produce the products on the right side of the arrow. Okay, so when we write chemical equations, one thing and one very important thing that we need to keep in mind and to pay attention to is probably one of the more important laws in chemistry and in science in general, and that is known as the law of conservation of matter. We saw this law earlier on in the semester. Okay, and again, just as a quick summary of this law, matter cannot be created nor destroyed. terms of our chemical equation and in terms of a something that is going to be applicable to us is the following. So for our equations, our chemical equations, the number of type atoms on the reactant side, on the left side. So that's an L, the left side, must equal the number and type of atoms on the So for instance, as a just a general statement. So if you start with, let's say 5 oxygen atoms, atoms, guess what? You must end up with 5. Right, so they're not created or destroyed, but they can be combined with other things to make new substances. That's the hallmark of chemical reactions, chemical changes, but they need to be there. So what we're going to do is we're going to do a little bit of chemical accounting in the next section. When we account for our chemicals, and specifically now what we're looking here is looking at our atoms. We're going to do something called balancing our equations. So we must balance our equations. Okay, that is a ramification of the law of conservation of matter. So if we go back to the example that we looked at before, and I'm going to omit the state symbols just for simplicity's sake. So I have my hydrogen reacting with oxygen to produce H2O. You may look at that and think, well, wait a minute. I'm starting off here with, if I look at my hydrogen atoms on the left side, so if I do a quick list, on the left side here, I have 2 H's and I have 2 O's on the left side. On the right side, I have to have H's and O's as well, right? So they don't just disappear. So on the right side, I have 2 H's and I have just this 1 O. Remember, you don't see a subscript. 1 is understood to be there, so I have 1 O on the left. So I have 2 hydrogens to start with, 2 to end with. I have 2 oxygen to start with, 1 oxygen to end with. This is not balanced. Okay, because I don't have the same number and types of atoms on either side. So what we're going to do to balance our equation is, so in order to balance equations, what we're going to use are things called coefficients. Okay, and again, another example where we have a big fancy word that means something very simple. What these coefficients are just simply small whole numbers, small integers, in other words, placed in front of the chemical formulas in order to balance our equation. And then what this means is that everything in the formula gets multiplied by that coefficient, whatever that coefficient is. Okay, and when it comes to balancing equations, like how are we going to know which coefficient to use? Really, what this boils down to is just trial and error. Okay, so we're just going to try some coefficients, see if they work out. Now, it's not just a random process because there are little hints and strategies we can use, and we'll talk about a few of them as we go through this process. All right, so what I like to do is when I balance my equations is I like to draw a little line in front of my chemical formulas so I know where I can place those coefficients, all right? So what students are often tempted to do is to change subscripts. We're not allowed to do that. Okay, so we cannot change subscripts because then you change the chemical identity of that substance. And you cannot insert coefficients in the middle of formulas. Okay, so we can't, for instance, change if I wanted to make two oxygens on the right side here. I couldn't just say, you know what, I'm going to change the subscript of 1 to 2. No, that is not allowed. You can't do that because then it's not water anymore. Then it's hydrogen peroxide. Similarly, I can't put a 2 in front of the O like that. That just doesn't look right, and it's actually very, very wrong. Okay, so what I can do in order to make two oxygens on the right side, what I need to do is to now put a coefficient in front of the thing with the oxygen to make two of it. Well, right now, there's one O, so 1 times something needs to give me 2. Well, obviously here, it needs to be 2. Okay, so 1 times 2 gives me the 2 O's, but what I've done is I've now also changed my hydrogens because water is made up of H's and O's. So now the 2 times the 2 would give me 4 H's. Okay, so don't forget when you put that coefficient in front, everything in that formula gets multiplied by that coefficient. So when I go back now and I can see, well, my hydrogens are out of balance. I have 2 on the left side. I need to now have 4. Well, 2 times what gives me 4? Well, 2 times 2. So that's going to give me 4 H's. I still have my 2 O's. Right, when you don't see a coefficient, 1 is understood to be there. You can put it in or you can leave it out. Just don't put 0. Okay, so 2 times 1 is going to give me my 2. We balance my O's to begin with, and then we balance our H's. This then is going to be our balanced equation for this reaction between hydrogen and oxygen to produce water. Okay, so this is a very simple example of balancing an equation. We're going to take a look at some other more challenging ones here in a second.